A balanced space X is defined to be reflexive if the natural embedding of X into its double dual X double star is surjective. So if X is in script X, then the image of X in this double dual, we call it X hat, is defined by X star, comma, X hat equals X, comma, X hat, X star for all X star in script X star. So this defines X hat. You know, X hat is a member in the double dual. So it's as a functional, it has a value on X star. And this value on X star is defined to be the value of X star on X. So recall that the map X maps X star, X hat is an isometry. Actually, this is a theorem saying that for each X in the balanced space X, there is a X star such that the norm of X star is 1. And the value of X star on X is the norm of X. So yeah, this we say it is an isometry. This comes from the statement I just said. Okay, so now if X is considered as a subspace of X double star, it is considered as a subspace of X. So X is contained in this X double star because we have a natural embedding of X into this X double star. Then the weak star topology, this is a weak star topology on X double star when restricted to X is just this weak topology on X. So this just comes from the definition of weak star topology and the weak topology. A simple way to think about this, to understand this, is that by this topology, the restriction of this topology on X, this topology is originally a topology on X double star. Since X is embedded into X double star, the restriction is a topology on X. Okay, this topology on X is defined by the family of the seminorms induced by elements in X star. And the same is true for this. Yeah, the topology on this is defined by a family of seminorms induced by elements of X star. So that's why the restriction of this is the same as this. So now, proposition 4.1. If X is a normed space, then ball X is sigma X double star, comma X star. In this topology, dense is dense in the ball X double star in this topology. Proof let B be this topology closure of a ball X in X double star. Okay, by a Lagrange theorem, this ball is closed, this topology closed. So it is because this ball is in this topology is compact, so it is closed. So, and this is the closure of this set. Okay. So the closure is the intersection of all closed sets containing this set. And this set is a closed set containing this set. So this set is a set in the intersection. So that's why B is contained in this. Okay. So yeah. So B is the closure of ball X. This is a closed set containing ball X. So B is contained here. We want to prove B is equal to that. So we use proof by contradiction. Suppose B is not equal to that, then there is a W in the set this minus B. Okay, if these two sets are not equal, then there's a W in the complement of B in this set. By theorem 1-3, for each this continuous linear functional L on X double star, there is an X star in X star such that this L is given by X star. So let's see. Yeah, theorem 1-3 says that if we use this topology on X star, theorem 1-3 says that if we use this topology on X double star, then the set of continuous linear functionals just the X star. So that means, which means each continuous linear functional on this X double star is given by a vector in X star. So this is theorem 1-3. So now we have the situation that you have a convex set, compact set. No, yeah. Yeah, this B is not only closed, but it is compact, okay? Because this set is compact by Lagrange theorem. So we have a convex compact set B, and we have a point outside B. Then by theorem 439 for the real functionals, real spaces, And 4.3.13 for complex spaces. By this theorem, if you have a compact convex set B and a point outside, we can have a functional separate the point and the set by these two theorems. Okay, one is for real, one is for complex. So if you have a point and a compact convex space, there is a linear functional to separate the point and the set in this sense. So the real part of x, comma x star is less than 1 plus epsilon, less than real part x star minus w. Okay. This is true for all x in ball x. Actually, if we look at the statement of the two theorems on page 111, we don't have 1 here. We only have a positive number alpha here. How can we get 1 here? We just multiply w and x star. We just multiply we just multiply the x star by a suitable constant. We can change this alpha to 1. Okay, so by the two theorems, we have a positive number alpha here. So we can multiply x star by a suitable constant to get 1 here. But now, so this is true for real part. But for any x in ball script x, we can multiply by a number in this form, e to the I theta. Theta is a real number, so this is a rotation. If we multiply x by a suitable complex number of absolute value 1, then we multiply by this for suitable theta, then we can make this inner product positive. So when you make this positive, the real part is the same as that. So real part becomes the absolute value. So the absolute value of the inner product here, this is not really inner product. This is the value of the functional on x. If we multiply x by e to the I theta with a suitable theta, we can make this real part equal to the absolute value. So this is less than or equal to 1 whenever the norm of x is less than or equal to 1. So this means, this implies the norm of x star is less than or equal to 1. That is, x star is in ball x script x star. So now let's look at this part. Let's look at this part. Of the inequality. Okay, so we have this 1 plus epsilon is less than the real part of this. So x star has absolute value, norm has norm less than or equal to 1. This W also has a norm less than or equal to 1. So this is less than or equal to 1. So we get 1 plus epsilon is less than or equal to is less than 1. So this is a contradiction. Okay. So let's look at this statement again. We have proved this. Let's review what we have proved. We have proved that the ball X, when embedded in ball X double star, this is a subset of ball X double star, and this is dense here in this ball X double star in this topology. Topology is defined. So to understand topology in this form, we just remember this topology are defined by members of X star. Members of X star. Now we come to the central theorem of this section. Central theorem of this section. So if X is a Banach space, then the following statements are equivalent. A, X is reflexive. B, X star is reflexive. C, sigma X star comma X equals sigma X star X double star. D, ball X is weakly compact. So let's see that our proof goes this way. We are going to have a simple loop to prove this. We prove D implies A, and A implies C, C implies B, and B implies D. So we have a simple loop to prove the theorem. So D implies A. So we have an observation before 4.1 at the beginning of the section. This observation says that the restriction of this topology to X is equal to the topology sigma X X star. This is originally, this is a topology on X double star, but X embedded into X double star is considered as a subset of X double star. So you have this restriction. The restriction of this topology equals to the topology on the right side. So to understand this, the simple way to understand this is this. This restriction topology is defined by members of X star, and this topology is also defined by members of X star, so they are the same. Okay. By D, D says ball X is weakly compact. This means weakly means the weak topology. Weak topology just means this topology of X. Okay, so assumption D says X is weakly compact. That means X is compact, ball X is compact in this topology. But this topology is the same as this topology. So ball X is compact in this topology. Compact must be closed. So this ball X is closed by this topology. But we also, previous proposition 4.1 says ball X is dense in this. And it is dense in this, and it is closed. So ball X is equal to ball X double star. Okay, so if then this clearly means that X is equal to X double star. So X is reflexive. So so here D implies A is because ball X, let's think again. Okay, ball X is weakly compact. So ball X is compact in this topology. But these two topologies are the same. So X is this topology compact. And the compact must be closed. So this ball X is closed in this ball X double star in this topology. But the previous statement says it is dense. Now we say it is closed. So these two must be the same. So X is reflexive. Now we see that A implies C. A implies C. C says these two topologies are the same. So this is clear because A says it is reflexive. Reflexive means X is equal to X double star. So then here X can be replaced by X double star. So that's why these two topologies are the same. Then we see C implies B. By Lagrange's theorem, ball X is compact in this topology, okay? But this topology is the same as this. So ball C by C, ball X star is compact in this topology. And the compact must be closed. Okay, okay. So we can see that ball X double star by Lagrange's theorem, ball X star is compact in this topology. But by C, this topology is the same by this topology. So ball X star is sigma is compact in this topology. But we say the ball X star is compact in this topology. This just says that ball X star is weakly compact because this is the dual of X star. This means X star is weakly compact. Since it has already been shown that D implies A. D implies A means if a space is weakly compact, then it is reflexive. Now, ball X star is weakly compact, so X star is reflexive. So we have proved C implies B. Finally, we are going to prove B implies D. Okay. So now let's recall the observation before at the beginning of the section. It says that the embedding from X to X double star is isometric. This means norm invariant. Okay. Since this is norm invariant, the ball X, because X is a Banach space, that means it's complete. So ball X is a complete set. So after embedding, it's still, because it's isometric. So after embedding, it is still a complete set. If it's so this is a complete set in this space. Any complete subset of a metric space must be closed. So it is a norm closed. Okay. Yeah, this is any complete subset is closed. Because if you have a point which is the limit of a sequence in this set, then this sequence must be Cauchy. But since it's complete, the limit must be contained in this set. So the set is closed. So this ball X is norm closed in X star, X double star. If it is norm closed, that means it is closed in the topology, original topology of X double star, in the natural topology of X double star. So, but by corollary 1.5, since this set is convex, if it is closed in the original topology, natural topology, it must be closed in the weak topology. The weak topology is this. So ball X is closed in this topology. But by B says that this is B implies D. B says X star is reflexive. That means X star is equal to X triple star. So here, X triple star can be replaced by X star. So this says that the ball X is closed in this topology. But this topology, so this set is closed in the ball. Yeah, I forgot to put ball here. Ball X double star. Okay, this is closed in ball X double star. But by Lagrange theorem, ball X double star is compact in this topology. So now you have a closed subset of a compact set. So this set must be compact. So the ball of this is compact in this topology. But as we mentioned earlier, this topology is the same as the topology sigma x star. When restricted to x, this is the same as that. So ball X is compact in this topology. That means it is weakly compact. So this has been proved, except that we should put ball here and ball here. Okay. If we add these two balls here, then the proof is complete. So we have, this theorem has been proved. Corollary 4.3 says that if X is reflexive Banach space and M is a closed subspace, then M is reflexive. Okay, this proof is just the proof is short. Okay, so ball of M is just this M intersect this. So ball M is sigma x star compact, because this is compact. This is a closed set intersect a compact. So a closed subset of a compact set is compact. By Hahn-Banach theorem, each functional M extends to X. So the intersection, the restriction of this topology on M is equal to just this topology. So we say this is ball M is compact in this topology is the same as saying ball M is compact in this topology. So ball M is compact in this topology. So this means ball M is weakly compact. So by the theorem, M is reflexive. So now a sequence Xn is in X is said to be a weakly Cauchy sequence if for every X star in X star, this sequence of scalars is a Cauchy sequence in F. Proposition 4.3a. But this is, we have, this, the statement in proposition 4.3a is used several times implicitly. So let us just state here so that we know what is going on. Okay, a sequence xn in a locally convex space X converges to X weakly. Weakly means in the weak topology. And this is, okay, when you have a topology, there's a concept of convergence. So the sequence converges to this weakly means it converges in the weak topology. And this is true if and only if for each X star in script X star, this limit, this sequence of scalars converges to this scalar. Corollary 4.4. If X is reflexive, then X is weakly sequentially complete. We didn't define what is weakly sequentially complete. Now, what we say below is just a definition of this weakly sequentially complete. So X is weakly sequentially complete in the sense that every weakly Cauchy sequence in X converges weakly. This means that if every weakly Cauchy sequence converges weakly, we say it is weakly sequentially complete. And this X is weakly sequentially complete. So to prove this, we just have to prove that every weakly Cauchy sequence converges weakly. That's what we have to prove. Okay. Now suppose there is a sequence which is xn, which is weakly Cauchy sequence. That means for each functional x star, this is a Cauchy sequence of scalars. So therefore, for each x star, this sequence of scalars is Cauchy, so it must be bounded. For each x star, this sequence of scalars is bounded. So yeah, in this case, we say this xn, the sequence is weakly bounded. Weakly bounded just means for each x star, this sequence of scalars is bounded. This scalar sequence of scalars is bounded because it is a Cauchy sequence. The Cauchy sequence is convergent, so it is bounded. So this sequence is weakly bounded. By the principle of uniform boundedness, there is a constant m such that Mn, Xn norm is less than or equal to m for all n greater than or equal to 1. This just says that if Xn is weakly bounded, it must be norm bounded. We didn't use these terms when we stated the principle of uniform boundedness, but that principle is just this, okay? If it's weakly bounded, then it is norm bounded. Okay, so, but this is weakly compact since X is reflexive. We just proved that, okay? Theorem 4.2. If X is reflexive, then this is weakly bounded. Reflexive is condition A, and this is weakly compact is condition D. Remember that. Weakly compact. So means this sequence is compact in the weak topology. So since it is compact, there's a subsequence which converges in that topology. So there's a subsequence converges weakly to a vector X in script X. Okay. So for each X star in script X star, this exists. This sequence of scalars converges to converges. So the limit exists because we know this is the Cauchy sequence. So the limit exists. On the other hand, the subsequence corresponding to this, first we know the limit exists. Secondly, we know a subsequence converges to that. So the whole sequence converges to that. Okay, so the whole sequence is convergent, and the subsequence converges to a limit, then the whole sequence must converge to that limit. So this means for every X star, the sequence of scalars converges to this by the definition or by proposition 4.3a. This means Xn converges to X weakly. So corollary has been proved. So we have proved that if the space is reflexive, then it is weakly sequentially complete. That is not true for all general Banach spaces, i.e., not all Banach spaces are weakly sequentially complete. So we are going to see an example to illustrate this point. Yeah, we stop here. We continue next time.